Hello, everybody. Let's get started. So we are moving along in the course, and I do want to tell you that as hard as it seemed recently, that as we get towards the end of the semester, this lecture and the last few, it will get easier. You'll notice that the study guides or those lecture handouts, outlines are getting shorter. So you are getting there. So hang in there. So we're going to move on to antimicrobial treatments. So when we think about antimicrobial treatments, we are literally running what we call a co-evolutionary arms race with the germs in our environment, right? So when we think about those times when the microorganism now is outcompeting our native organisms, so we have our own microbiomes that have taken up residence in our body, and by them being there, they protect us. But occasionally we know that a more virulent strain has taken up residence, or our own bacteria have overpopulated, perhaps because our immune systems are down, or as a result of acquiring a secondary infection after a primary infection. So we are essentially at risk of becoming overpopulated by microorganisms. So when we think about those times when you might have had an ear infection, sinus infection, maybe you've traveled to another country and you picked up some kind of dysentery from some microorganism, often a non-native E. coli strain, then you might need some medication. So let's take a look at the characteristics of an ideal antimicrobial drug. And then we're going to move into how they were discovered, how do we know that there's chemicals there, and how do they work. All right. So when we think about this, again, so we want to take a medication, an antimicrobial drug, that is only affecting the microbe that is causing the problem. So in your book, they call it an antimicrobial drug should be toxic to the microbe that is causing you the infection, but non-toxic to your host cells. So when we start to think about this, we have to think about drugs that are going to target something about the bacterium or something about a virus, or if we're talking about protists, or if we're talking about worms, we need to target something unique about the cells of the actual microorganism that is causing the infection. Okay, so that's tricky, as you might imagine. It's easier to treat bacterial infections than it is eukaryotic infections, so like a fungal infection, because human cells are eukaryotic. Fungal cells are eukaryotic. So we have to find something that's different about the fungus to attack. So something about that cell wall, something about the metabolism or something like that. Okay, so we want to make sure the antimicrobial drug is only toxic to the causative agent of whatever your infection is and not your host cells. Second, we need something that's microbicidal, not microbistatic, because we need to lower and eliminate as much as possible that disease-causing microorganism. We don't want to just kind of put it in stasis, just kind of reduce it, and just kind of keep it there, right? That can happen if we're taking the wrong antibiotics. We'll come back to that. Okay, third point. We want these antimicrobial drugs to be relatively soluble and functions even when highly diluted in the body fluids. Okay, so think about it. If you're taking a Z-Pak, or if you're taking an antifungal twice a day, we need to make sure that that medication, whatever concentration it is going to work in the body once it's gone through what we call the secondary pass. So it usually goes to the liver to be metabolized. But we want to make sure that even when it's diluted, it's still going to be effective against that infection. Fourth, remains potent long enough to act and is not broken down or excreted prematurely. So if you're taking a medication that's not hanging around long enough to kill, let's say, bacterium, that bacterial population, and it's just kind of going in and out of your body, it's getting flushed out by your kidneys, then it's not having long enough effect to reduce that overpopulation. Next, does not lead to the development of microbial resistance. So we know that this is a serious side effect, if you will, of taking antimicrobial medication, is that those microorganisms, if they're being exposed to the same antibiotic over and over and over again, that there can be some of those cells that are not dying from the antibiotic. So they are repopulating, and so causing a more virulent infection. And it can also mean that whatever worked for you in the past, whether that's amoxicillin, for example, now you have to take something that's a little bit more targeted to the microorganism that you are harboring. All right, next. The antimicrobial drug should complement or assist the activities of the host defenses, right? So we have this incredible immune system. We've got the macrophages, we've got cytotoxic T cells, we have natural killer cells, and it goes on and on and on. So we want to make sure that we're working with the immune system so that essentially as we're lowering that microbial population, sometimes the immune system can take over and kind of finish it up. So we don't want to be do anything that's going to compromise the immune system from doing its fantastic job that it does. Next. So this antimicrobial drug should remain active in tissues and body fluids. So they will sometimes tell you, okay, so you're going to take this medication twice a day for 10 days, and then they will tell you it will still remain effective for another 10 days or another 5 days or 7 days afterward, okay? So this means that you're taking the medication, it's in the body, and it stays in the body a little bit longer without you even taking the medication. And again, assuring that we're lowering and hopefully eliminating that high microbial population. All right, next, readily delivered to the site of infection. So this one can be a little bit trickier. So if you have an infection in your lungs, maybe you have a biofilm like Pseudomonas in your lungs, to just treat the whole body with this antibacterial medication may not do the trick. We may actually have to get some of that medication directly to that biofilm in the lungs. So something to think about. Not everything is readily treated just by taking oral medication. Sometimes we need IVs. Sometimes, like with wounds, we might need direct contact of things like Silvadene or that silver compound that can help reduce bacterial infections and wounds. Next, be safely and easily broken down and excreted. So we don't need any confounding factors. And we're going to come back to this. So when a physician is looking to prescribe an antimicrobial drug to an individual, there's a lot of things that they have to take into consideration. And certainly one of those is liver health and kidney health, okay? First pass effect is when the medication goes to the liver and it's actually metabolized, and then the medication is free to have its effect. Then a lot of our medications are going to be excreted through the kidneys or through the feces, but we think about kidneys and those individuals that have kidney damage. Yes, of course, we're going to be careful about giving them an antimicrobial drug that needs to, work by the kidneys. So if the kidneys are compromised, then they might think about some other antimicrobial drug. The other thing you might hear is, what are your allergies? What are your drug allergies? I do want to make a comment about allergies. So we know that there's like a clinical definition of allergy. So if you have a peanut allergy, you may have anaphylaxis from that allergy. So when we think about allergies, we think about that anaphylaxis, trouble breathing, systemic life-threatening side effects. When we think about having a sensitivity to something, so I've taken a medication and then kind of broke out with some hives. So that's sensitivity, right? So I can get stung by a bee and have a pretty huge localized reaction. It's a sensitivity. It's only when it becomes compromising to your respiratory system and systemic effects that we're going to think about it being a true allergy. Having said that, when you go to the hospital, they're still going to say, what are your allergies to medications? And so these will be any medications that just don't agree with you. So I just want to point that out. So sometimes people are, in fact, sensitive to a variety of antimicrobials, and that should be acknowledged. But again, physicians will also oftentimes do this risk analysis. Does the benefit outweigh the negatives? Okay. All right, next. Does not disrupt the host's health by causing allergies or predisposing the host to other infections. So we just talked about that a bit, and we will move on. All right, there are some terms that you're going to run into, so I want to go ahead and address this. Prophylaxis. So you might have heard someone say, oh, I'm on a prophylactic antibiotic for UTIs. My dog right now is on a prophylactic antibiotic because she's having recurring UTIs. She's 15 years old. So essentially we're trying to, let her live the best health that she can in her latter years. So this is the use of a drug to prevent infection of a person at risk. So sometimes people are on prophylactic antibiotics without essentially a diagnosis of an acute antimicrobial infection. This is to prevent infection. All right. And next, antimicrobial chemotherapy. So this is where you have an infection and we're now using medications to control the infection. Antimicrobials. You might recognize that in the previous slide and on this slide, it uses this word, this catch-all term, antimicrobials. What this refers to is essentially drugs that are active against bacteria, fungi, protists, and viruses. So this is any of those microorganisms we're thinking about in microbiology. If we're thinking about exclusively bacteria, then we're thinking about antibiotics. Okay, so that's used for those drugs that we're using to target bacteria and not the other types of microbes. So hence we have antivirals, antifungals, antiprotozoans or antiprotozoals, that kind of thing. So antibiotics is only drugs that are going to target bacteria. All right, then we have semi-synthetic and synthetic drugs. And as you might imagine, when we're thinking about synthetic, we're imagining that humans have altered something in some way. So a semi-synthetic drug has been altered after being isolated from a natural source, and we're going to talk about some natural sources in the next few slides. And then we have synthetic drugs that generally are being inspired by, if you will, those natural sources, but have been augmented in some way and completely created in a lab. So those are our synthetic drugs. Then we have narrow spectrum and broad spectrum. So broad spectrum is generally what we want to use when we're not quite sure what infection you have. So you might go into the hospital. I know from my dad's experience, he would go into the hospital. He would have pneumonia. And so they would put him on a broad spectrum antibiotic, and then they would ask him to essentially collect some of his sputum in a collection or a specimen cup, and then they could do culture and sensitivity. Once they figured out what was the causative agent of his pneumonia, then they would put him on a narrow spectrum antibiotic. So we're thinking about broad spectrum. The example here is a drug that's against both gram-positive and gram-negative bacteria, whereas a narrow spectrum would target just one or the other. I have another minute left. I want to tell you about the discovery of the first antibiotic by Alexander Fleming in 1928. Essentially, he was a microbiologist and he was culturing bacteria. If you look at this petri dish on the left-hand side, this is oftentimes what you will get when you are sampling bacteria from nature. So it is not a pure culture. You can see, you can identify several different kinds of colony types. But what he noticed was around some of these colonies, you could see a clear area. So this is called a zone of inhibition. So this is a little narrower, this is a little broader, this is a little broader. And so what he discovered is that the zone of inhibition, which was killing bacteria, was resulting from this fungus. The fungus is called Penicillium, and the Penicillium makes its own natural antibiotics to kill other bacteria from outcompeting it. So this was essentially isolated and termed, this term that we know, penicillin, comes from that fungus called Penicillium. We will pick up in the next video, so I'll see you there.